you know, I like to think you guys all go and review and study, and that's why I give you a chance.
On the last homework, chapter 26 through 27, question 13, it says, is the wavelength of light longer or shorter in water compared to when it is in air?
So last homework, just read that again, is
the
wavelength
of light longer or shorter in water compared to when it is in air?
The wavelength of light in water versus air. Good. I'm glad you brought that up. What does change when light goes from air to water? It's speed, it's velocity. Very good. That's very good. So, I should have went the other way. A little higher to see the board. Instead of just giving you the answer, I'm trying to, so you can reason it out yourself next time. Yeah. So this is changing. So one of these must be changing. And this is good because last lecture we did mirrors, reflections. And today we're going to do more about refraction and going through. And let me ask you this. When you look at yourself in the mirror, do the colors change? No. So what does that refer to? What's the color of light dependent upon? In that light wave. What determines something's color? The frequency. It's the vibration of those atoms or electrons. How fast, that's the source of electromagnetic radiation. So that frequency determines what color it is, whether it's in the visible range or outside the visible range. Remember, most of the electromagnetic spectrum is invisible to us. We could say it has color, you know, like radio waves and microwaves, but we can't see those. So that's an indicator that the frequency does not change, which would hint that the wavelength does then. That's what we saw with sound waves, and it applies in refraction also, when you go through something. If I look at you through a piece of glass, does the color change? No. So again, the frequency isn't changing, but it does slow down in the glass or the water. So the wavelength must be, if it slows down, velocity gets smaller, so wavelength gets shorter. No. This is a smaller number. It's not going as fast. This will change size. Okay, now you had something else to add. So bottom line there is very good. I want you to know that speed changes when light refracts. That's why it refracts, actually. It wouldn't refract if the speed didn't change. Since we're on it, I'll do that demo now. Here's a container of water, and this one's empty. And I'll flip it over so you can see the water fall to the bottom side. I have a wire mesh in here because you probably noticed by now, hey, wait a minute, there's something in there, and I didn't want them to fall through. So I'm shaking to let the water get down to the bottom. Those were there all along. They're those, they've been popular the last few years, spit wads or grow spheres. Have you ever had those little things? They start out like this big, and you soak them in water for hours or days, and they get bigger because they absorb the water up. Well, they are mostly water, 99.9% water. Well, what happens when you put water in water? Can you see it? The speed of light travels the same in water, and then when it transfers to water, it's going the same speed. So it doesn't bend. There is no refraction if it doesn't slow down or speed up. Thus, the light's not slowing down or speeding up as it goes from water to these bags of water. So watch again. I'll flip it over and watch the spheres. It's like magic. They disappear. They're still there, but we can't tell because no light bends from the edges to give us a clue. The light that comes from back here doesn't get bent. It comes straight through. So you can't tell the spheres are there. I think that's cool. That's how the invisible man would be. You know, if you wanted to be invisible, light would have to travel, well, one way is light would have to travel through you at the same speed it does in air, so it doesn't get bent. Then nobody could see you. That would work. Can you think of a problem with that? If the light that enters you does not get bent, others wouldn't see you, but what else would happen? Think about how you're able to see in the first place. Yeah, light goes into your eyeball. And normal people, when light goes from air to water, your cornea, it refracts and bends because it's slowed down. Light from this side might bend that way, and light from this side might bend that way. And they come to a focus on your retina. We discussed that. And that's how we form images. So, if you were invisible, you would have to be blind. Because if the light's not being bent, and you can't see me, then I can't see either because it's not focusing. Unless you got two floating eyeballs. You could be invisible except for your eyes. But we'd have to be able to see them. I find it interesting, most Hollywood get that wrong, of course, because you don't want two floating eyeballs. But there was a television show several years back with some invisible person. I didn't follow it, but I remember he did get headaches or something because it was messing with his eye. He couldn't be invisible very long because it messed him up, kind of with his vision. So at least they were getting closer. Let's make these disappear again. Ready? Okay. You can try this at home. You can buy these yourself, but Pyrex glass, like your Pyrex measuring cups, and Wesson cooking oil, corn vegetable oil, most brands, but I like Wesson. The speed of light goes about the same velocity through both of those. So if they were together or next to each other, you wouldn't see the bending, or it'd be very, very slight because it's nearly the same speed. What that means is you can pour a jar full of oil, and then put your measuring cup inside. If it's Pyrex, the glass will look like it just disappears. And all you see is the writing on it. Or, if you have your cup and you fill it full of some oil, well, now you have oil, an oil-glass interface. That will disappear because there's no refraction there. They're going the same speed. And so it'll kind of look like this. It'll look like the walls went away. Anyway, try it at home. Refraction occurs because of change in speed. If there is no change in speed, there's no refraction. You want something to bend more? Slow it down even more, or speed it up even more. Cool. Let's do some clicker questions. Review a few reflection things from last time. All right, wake up. Come on. All right, there's the session ID number in the bottom right. And I remembered to plug in the receiver this time. While you're logging in, just to stall. So today, I'm still on chapter 28 with refraction. Wednesday will be chapter 29 with diffraction. Not refraction, but diffraction. We'll review Friday. Fill in any holes or whatnot. And the exam on this stuff is next Monday, so a week from now. You have one more homework assignment, which is now on this stuff. And it will be due, though, you listening? Friday night. Not Sunday night. Friday night. And that's because if I did it Sunday night, you'd only have the Monday morning to check the answers and study for the test. And I don't want that. So your homework this time is due Friday. Okay. Light takes the path from one point to another that is quickest, shortest, closest to a straight line, or none. Looks like the majority, so I'll get the rest of you in. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, we're split all over the place. Quickest, shortest, and closest to a straight line. Somebody thinks none. This was a principle that it's in your text and I introduced last time. I was trying to draw the pictures off of reflection. You could go from point A to point B, but if you have to go off of a mirror, it can take multiple paths. But does it want the shortest path or the quickest path, or is it just forget the mirror altogether? But if it's reflecting, you kind of have to involve the mirror. So I'm giving you a hint. It's A or B. Discuss that with your neighbor. I'll reopen polling. Let's see if that changes any of your minds. The shortest distance or the fastest time? That's what we're deciding on here. Did that jog anybody's memory from last lecture, I hope? You drawing those pictures?
So my phone deleted the app, and I don't know my login info. So
You forgot your login info?
I'm trying to figure that out in the next few minutes. It may take a while.
We'll write them on a piece of paper too as we go. You can at least turn that in. All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Nope, you guys are still split. Okay, so that should be an indicator to you to go look that up more in the either last lecture or your textbook. The answer is quickest. Whoop, not that button. That button. If that's A and B and this is a mirror, this is called Fermat's principle. And instead of having to pronounce his name every time, Fermat's principle. The principle of least time. The principle of least time. The paths of light always will take the one that takes the least amount of time. So, go home and draw this. If you go down first and then over, if it's traveling at a fixed speed, and you know the speed of light, you can measure that distance. That's a longer distance than if it went here, let's say, or there. And so the middle one is actually, in this case, the shortest distance, and that works out coincidentally with reflection. But I chose this specific question because a more general principle is true. Fermat's principle, the path of least time, because that works in reflection and refraction, what we're going to do more of today. That also allows it to, you get rid of the bad ones here. If I drew it anywhere to scale, remember if you draw your normal, this angle and that angle will be the same. The angle of incidence will always equal the angle of reflection. It was like pretending like you were going from a straight line to point B down here that might be an image. So it's like, if you will, if that helps you think about it, at this point it sees an image of B over here. And so it tries to go straight to it. But the mirror gets in the way, it reflects at equal angles and ends up hitting B. What do you know? Because this distance is the same distance. We discussed that too. When you look in a plane mirror, you see an image of yourself the same distance behind the mirror as you are in front. So, least time. Polling open, dim the light so you can actually see it. So what happens when light reflects off a polished reflecting surface? Let's see what you guys have learned from the text or already know and me. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, we got more of you. Well, that's great. Most of you think it partly reflects. That's correct. Well, as he says there, the fortune and fame await the discoverer of a surface that reflects all incident light. Don't feel bad if you didn't know that one already, but I want you to know now, every time light hits something, some of it gets reflected and some of it gets transmitted. If it goes all the way through, we call it transparent. If it gets absorbed, we call it opaque. But there's always, at every interface, some of the light reflects, some can refract into the material, be absorbed that way. For mirrors, most of it reflects. Roughly about 4%, though, won't. And your desk, it's pretty opaque. It absorbs most of it, but you can see a little reflection off of it, can't you? And the less polished something is, the less reflective it is. So even less light bounces off. I want you to realize both things always happen, at least in some amount, of every interface. And then one more I wanted to ask you guys. Go. So some things reflect better than others. I mean, we talked about specular reflection and diffuse reflection, and it was caused by something. But it's affected by these choices. I want to see if any of you caught that, or it stuck with you, or read it. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. The angle of the incoming light is the far majority's answer. Whether a particular surface acts as a polished reflector or a diffuse reflector depends on the angle. Well, good. See, I know. Now I know. I need to go over that more. Before I give you the answer, I'm at least glad you chose that choice rather than another wrong choice. So if it's polished, it's nice and smooth. And so the angle the light comes in at determines the angle it comes out at. If you're at a bigger incoming angle with respect to the normal, then it comes out at a bigger angle. But it's directional if this is perfectly reflective and nice and polished. And if the surface isn't, I'm exaggerating, but if it's rough or microscopically not smooth, then when the light ray comes in, this one still follows the law of reflection and reflects out at the same angle it came in at with respect to the normal. But the normal there is about like that. So that one's going to reflect back almost on itself. Another light ray, let's see where it ends up. Hope it hits there. It might be similar. Another one hits there. Oh, now the normal is about like that. So that one gets there. I think you get the idea. That one does kind of come back on itself. And so they do reflect, but in all directions. They get scattered. And this light is more diffuse because it's spread out. So one thing that affects the amount of reflection is this surface, how smooth it is. The second thing, which answers this question, is the light that's coming in, the size of its wavelength, which in this would be what color it is, the frequency. Red light has a longer wavelength, a bigger wavelength, because it's vibrating more slowly. And this is how I remember it. Big waves, if they're big compared to this size, they don't get affected as much. But a little guy, he's now comparable to size. He's going to get affected more. And that's true. So the longer the wavelength, the less scattered it gets. We discussed the brain lapse. Radio waves, yeah, with the satellite dishes. That's the word I was looking for. You know, they try to focus some light. If this was a mirror, you know, light's coming in, they'll reflect through a focal point. If this is specular reflection, if these wavelengths are big compared to the smoothness of this. Radio waves are really big. So this doesn't even have to be a mirror. And you look at big satellite dishes or your cable antenna, you don't see a reflection in it. To visible light, which has really small waves, your dish is rough, and so it scatters. But radio wave, yeah, go ahead. For which kind? Yeah, gamma rays, very good. That's the extreme on one side of the electromagnetic spectrum, and they have a really short wavelength. So yes, to reflect those, to have specular reflection for gamma rays, yeah, it would have to be microscopically very smooth. Yeah. But for radio waves, which are huge, eh. What material could be that smooth off the top of my head? I don't know, actually. Yeah. So, the surface, but also the incoming color. It's traveling at a certain speed, so it has a certain frequency and wavelength. And bigger waves are affected less. Okay, you can put your clickers away. I'm done with that. We have 15. So I'd like to show you more refraction now, more examples about that. Let's say that's a piece of glass or plastic. We'll just call it glass. What the hey? Air, glass, air. This is point A, and this is point B. The shortest distance from A to B is like that, correct? But it's not the fastest. Why? Oh, that was to him? Okay. What happens when it enters the glass? It slows down. So yeah, this is nice. That's going fast. But now it slows down. So if we could make that distance any shorter, that would work. Can we? Could it go through this in any other spot or angle and be shorter than that distance? Like from here to there. I'll just come over here. We'd have that. What if we went that way? What if we went this way? What if we did a curve? I don't know. Maybe like that. All other paths would be longer and take even longer. So, if you shine light straight through a parallel pane of glass, that is the fastest way from A to B. So it goes straight through. Look at it this way too. What's the angle of incidence? Let's draw our normal to the surface, right? There is no angle. So there's no refraction. There's no bending. It just goes straight through. But again, one way to think of it is the amount of the least time, the principle of least time. You with me? Trying to give you a few ways to figure out on your own how this light's going to bend. But what if we had point C? There's a nice straight line. Again, it's going slower from here to here. That we could make shorter, couldn't we? We could go straight across, like that. Well, then go, because it would get bent there and you'd miss it. But maybe we could go straight across up here. Something like that. And that's roughly the idea what goes on. Let me thicken that one. It doesn't have to go straight across. That depends on your thickness. But my point here is it takes a little longer in the air here so that it can go a shorter distance in less time through the glass where it's slower. Do you remember my beach example from way back in the sound waves? With a lifeguard saving somebody? Let's see. Help, help. Okay. The lifeguard could go straight towards the person, but he swims more slowly in the water. So to get to the person fastest, he could go this way. Oh, but that's even farther through the water. So he goes a little further on the beach where he can go faster and then to the person. And there's some bending. That happened with sound waves. It also happens with light waves. It happens with all waves. It's to make it shortest. Now I want you to realize, and you'll see over there, it doesn't always have to go straight across. Because depending on the change in speed, maybe going like this. Could come in, and instead of heading that direction, it can still bend a little. And then instead of heading that direction, it'll bend the other way and get to the person. But it's not straight across, but that'll still be the fastest. Because sometimes if you make it straight across, you are increasing the distance in the air on the outsides, and that could make it longer. Again, it depends on the materials and how fast the change in speed is here. Let me show that with this. Somebody turned my power off. Excuse me. All right. Oh, look at this guy. Here's a piece of plastic. Ta-da! So this is the incident ray. It comes in. And can you see that instead of heading down this way, it gets bent, doink, refracts. But then at this interface, it happens again. Instead of heading that way, it doink, gets bent. Can you see the reflected ray a little here? So again, like that question, at this surface, this is mostly transparent, so most of the light goes through, but some of the light reflects here. And more of it refracts. And then on this interface, I don't know if it's as easily to see because it gets dimmer, but at this interface, we have refraction, and there is a little bit of light that reflects. Every time you hit an interface, there's a reflection and refraction. For reflection, you just follow the law of reflection. My hand's the normal. Can you see the incoming angle is the same as the reflection angle? I also want you guys to be more familiar with which way the light's going to bend when it refracts. When light goes from air into the glass, speeds up or slows down? Slows down. That should be your clue to which way it refracts. Do you remember my wheel axle demo? Rolling it. See, I drew a nice picture so I wouldn't have to flub this up. Here's my normal. Like if you're going from the sidewalk to grass, it's going to go slower in the grass, wheels. So let's see. Got light here. Some wheels rolling. This wheel runs into the grass first, and so it's going to go slower while that one's going faster as it crosses over. And what happens in real life if this wheel is going slower than that one? Yeah, it turns this way. That one's still going faster. That's how I always remember which way it's going. So instead of heading off in the same straight direction, it will get bent along that path. And it'll be more like this. Because now they're going the same speed and it'll continue in a straight line. Until, let's say it goes back to sidewalk. Let's draw our normal. This would be straight. Can you see that it'll bend the other way because it's the reverse? And so it'll end up bending away from the normal. Some of you might just memorize it. If you're going from something where you're traveling faster to slower, it bends towards the normal. From faster to slower, it bends towards the normal. If you go the other way, you go to something where it's now traveling faster, it bends away from the normal. And that's what we see over here. Here's the normal. So instead of heading off in this direction, it bends towards the normal and then away from it when it speeds back up. And that works for different angles. See, when you go straight through, it just goes straight through. Whee! Any questions about that? Works this way too. See the reflected ray and the refracted ray. So principle of least time still applies. Slows down. Glass for now. Just did that. Here's a classic example. You put an object in something, and the ridges in the glass are kind of curved, so you see it refracted. I hope the pencil to you looks like it's disjointed or segmented. That's because light's slowing down in the glass and gets bent. This tub of water, to some of you, the edges seen through the water don't look straight. They might go up and then continue. It's over there. I can put this in the water, and to some of you, it'll look bent. You've probably all observed this when you stick your finger in water or your friend's swimming. It looks like they have short legs. That's all refraction, just because this light's bending. Does it look bent to you guys? I hope. Good. Which way does the meter stick look like it's bent? Which direction does it look like it's bending? It's heading down in this direction, and then does it get bent up or bend down to you? I heard one vote for up. I was just waiting for a few more. Is it up for you? Of course, this isn't always fun because see, you guys are at a lower angle, they're at a higher angle. It depends on whether you're seeing it from here or through here. But if you're looking from above on top, those of you that are higher up, to me, right now, it looks like the meter stick goes like this, hits the water, and then bends that way. It's like it's coming up. Well, what if you're shooting a fish? You see a fish under the water, and you want to throw your spear at it or a rock, or I don't know, maybe you shoot it with a gun. Yeah, shotgun. Well, I see the fish, in a spot over here, kind of higher up to the surface. The real fish, though, would be lower. Because light from that fish comes up, hits the interface, and bends away from the normal. So it's kind of like, let me draw it. That'll make this pointing stuff. You got happy fish over here. The light from that fish, say it's one ray comes up to here. Well, what happens? You draw the normal. You get a reflected ray, and his buddy sees him. Hello. But some of it refracts also. Which way will it refract? Away from the normal, because it's speeding up back into the air. So instead of heading that way, it gets bent this way. And if you're standing over here looking at it, you think the fish came from where? Up here. So you see the image of the fish up here. Does that make sense? And yes, sound effects help. So if you aim there, you're going to miss. Because the fish is down here. What if you shot a laser beam at it instead? Let's shoot light at it. Where do you aim? Here, or maybe lower? You aim where you think you see it? Rachel, you disagreeing? Well, let's see what happens if we aim where you think you see it. So you shoot your laser this way, right? And what does that beam do? It refracts in which way? Towards the normal. Hey, we got him. Because the light that came from the fish is being bent. If you're shooting light back at him, it's going to get bent the same amount. Convenient, huh? But if you're shooting a bullet or a spear, you see it in a different space. It's place. Overhead projectors have Fresnel lenses. They refract light. And I like taking them out just because they look funny. They refract and bend the light rays from off of my face. And so, tell me where it looks weirdest. Say when. Right about there? Okay, I'll just face everybody and talk. I probably look like I got like pizza face or something. Really big. But it's just because, what? It's just because the light's refracting. And that's how lenses work. You can bend it, make it look bigger, or you can make it look smaller, depending on the curvature of the lens or which way it's refracting. Wow. This one's similar. Tell me where it's good. Here, say when. About there. Same idea. A little closer? But you can have all kinds of fun. So if you're at a surplus store or something, yeah, grab one of these Fresnel lenses out of old overhead projectors. You can have fun with them. They're also really good. They focus a lot for a skinny amount. So you can focus the sun rays too to a point. And it's better than a magnifying glass if you get a big one. Oh, how about our atmosphere? Let's say you got the Earth, and you're standing here. Yay! Okay, that didn't work. We have an atmosphere, and the sun's over here. Light from the sun does not follow that path, because I bet you see where I'm going with this. When it switches from space to air, it refracts. In which way do you think it bends? Yeah, so if this is the surface here, and we have a normal, it's going to bend down. So where would the sun need to be for me to see it? Down here. So light would come to this point and refract down, and as it goes through the atmosphere, more of it kind of curves a little, because it's like a bunch of little, and you end up seeing the sun in your eyeball, and you think the sun came from, trace it back, up here. So when you see the sunset and you see it just go below the horizon, it already set. You missed it. That actually lengthens our daylight a little, because when we can see the sun below the horizon due to refraction in the atmosphere. I think that's cool. Okay, which way do you think light bends if you have warm air versus cool air? Which one do you think light travels through faster? That's going to matter which way it bends, doesn't it? Raise your hand if you think it's cool. Raise your hand if you think it's warm. We got more votes for warm. So you're right. That's because it's thinner. A warm air expands. It's less dense. And so there's less interactions. Light will transmit through it quicker. So the speed of light is actually a little faster in warm air than cold. So if you have light coming in like this, you draw the normal. Some of it might reflect at the same angle. But which way will it refract? It's going to speed up, and thus that axle, vroom, this wheel gets going faster. And so it bends away from the normal and heads that way. And this is the cause of mirages. Who's ever seen a mirage? I bet more of you have than you realize. Headlights, or the road that looks like it's wet up ahead, and then you finally get there and it's not wet. What's up with that? That's this idea. I'll draw the classic here. If you have a tree, okay, it's probably more of a palm tree in these situations, but if this gets really hot, the road, then it heats up the air above it, or heat transfer. So if this is warmer and this is colder, waves will come down into here and they get refracted. Oh, and I covered it up. Like that. So some of that light will head up. But as you get closer to the surface, it's even hotter, and so it gets bent some more, and some more, and some more, and it actually ends up doing that. And so if you're standing over here, you go, what? Because you think the tree came from down here. You see an image down here, and that's the mirage. If this was the hot road, what light's coming to you? Light off of maybe some car's headlights. Look next time. You can see two sets of headlights. One from the car and one below it. Or maybe there's no car there. The light came from the sky, the blue sky, and that's why it looks wet. And this works on the ocean too. Has anybody ever seen that? I grew up in Kansas, so I haven't been to the ocean much. But this is swapped. And so the light will go the other way. And you'll see this ship and another ship. An image of it on top of it, because it bends the other way. Some people have reported that out on the ocean. That's a mirage. Rainbows. No, let's do the lenses. Let's go back to this. This lens is curved. It's fatter in the middle. You can play the law of reflection and refraction again, which way it bends towards the normal and whatnot. But the bottom line is the rays will come together on a lens that's fatter in the middle. That's called a converging lens because it converges the rays together. Some people call it a convex lens because it's outwards, curved on the incoming light, like the mirror, the convex mirrors. This one's concave. Doesn't matter which way you turn this thing, because it's curved like this, like that concave mirror. It's also called a diverging lens because it spreads the light rays out. This one, if I were standing here looking at the light from the object, I could see an image of it back here where I think all the rays converge to. For this one, depends on where I'm at. If I'm back here, I can get an image that's bigger because those light rays seem to come from a spot way back here. But it's flipped. Do you see how the light rays switch sides? That's why lenses can flip the images. There's images of all of you right now on the back of my retina, back of my eyeball on the retina, that are flipped because of my lens. If I stand up here, They're not flipped. It's like that concave mirror. Those of you that took the time to look at it. If you were close, you were right side up. And if you got beyond that focal point, you were flipped. Lenses can do the same thing due to refraction. Yellow. So if we take this guy, different shape, it's still going to refract on each edge. So you get reflection, then refraction through it, then you get reflection off this side, and it refracts again. And I don't know how many of you can see it over here. Let me hold the piece of paper up. You get a rainbow. And why are the colors spread out? Do you remember why? What's the root cause of refraction? What's changing? The speed, right. Is each color going the same speed? One clue is since they're being refracted a different amount, no. We talked about this, it was several lectures ago. Blue light travels slower through the glass. It's got a higher frequency, and so it has more interactions as it goes through to slow it down. Remember, that's what slows light down, those interactions, absorbing it, re-emitting. Absorbing that, re-emitting, absorbing, re-emitting. Well, the more of those that occur, the longer it takes. So blue light travels more slowly through the prism, red faster. Since they're now traveling at different speeds, they get refracted different amounts. Does that make sense? And that's why you see blue on the bottom here, violet. It's getting bent more. It spends more time in the lens, so to speak. Well, actually it does. It gets bent more. We did it before with a prism over here. Let's see. And we got a rainbow over there. Same idea, this one's just prettier. But the light's headed that way. All colors get refracted, but violet gets refracted even more, the most, because it's got a higher frequency. Red less. And that's what causes rainbows. You got a water droplet. And the light goes into it a lot like this. It goes in one side and refracts. It reflects off the back side, comes back towards the front, refracts again, just like this, kind of like this. It spreads the different colors out, and you can see the rainbow. There's great pictures in your text. They'll draw it better than I do, of course. But this is the gist. If there's a raindrop, try to draw it right, and you got white light coming in, it will reflect. Draw your normal. You get some light that reflects. Well, that wasn't drawn the same angle, was it? But most of it will refract towards the normal. And then some of that will reflect, and some of it will refract away from the normal. And then again, some will reflect, and some will refract away from the normal. This is the one that's brightest, the one that keeps refracting, because raindrops are mostly clear. And so if your eyeball's over here, you think the light came from somewhere over here. You with me thus far? Yeah, the sun has to be behind you. And you see the rainbow on the other side. But just like the prism, blue light gets refracted more than red light. So if something gets refracted more, it's going to get bent a little more here, and a little more there, and a little different there. And the idea is red and violet and blue light come out at different angles. And so you see them as if they came from a different spot. There's your rainbow. one water droplet sends you one color. See, this one would miss your eyeball, wouldn't it? But maybe a water droplet above would come into your eye at that angle. And then you got all those water droplets. Forms a nice bow. It's really like a cone. And the rainbow you see is never the same rainbow somebody else sees, because they're standing over here. So they're getting colors of light from a different raindrop. You're seeing the one over here. Just go like this, and you're seeing a different rainbow. Doesn't look like it, but different light's coming at you. One term you should know, this is called dispersion. Dispersion. When the colors of light refract at different angles and spread white light into its constituent colors, it's called dispersion. You might as well know that. Okay, I'm out of time. We'll do more later. Have a great day.